This lesson deals with a bandpass filter. You can find these notes in the course ebook in Chapter 6 starting on page 9. Given this frequency domain circuit, can you solve for the transfer function V out over V sub S? Well, V out is equal to the voltage across this resistor, and we have series combinations. They all share the same current, so we could use a voltage divider. So V out is going to be equal to R over the sum of the impedances J omega L plus 1 over J omega C plus R. And that's this expression right here. Let's multiply numerator and denominator by J omega C. So I get J omega RC in the numerator. This term times J omega C is 1. Multiply this by J omega C, you get J squared, which is a minus 1, and omega squared and L times C. And then lastly, this times J omega C is J omega RC. This is the general form of a bandpass filter. And if you factor the terms in the equation in terms of two constants, omega naught and Q naught, you can interpret what's going on in the circuit in the Bode plot. Let me just give this as a definition. Now, if you compare the terms here with the terms here, we could solve for the two constants, omega naught and Q naught. Here's probably the easiest one. Here's omega naught squared. If I write this as 1 over LC, then omega naught squared is 1 over LC, and omega naught is 1 over the square root of LC. Then take a look at this term here. I've got omega and omega, then I've got RC, and I've got 1 over omega naught Q naught. So omega naught Q naught is 1 over RC, and now I can solve for Q naught. It's going to be equal to 1 over omega naught RC, but omega naught is 1 over the square root of LC, and I could write this C here as the square root of C squared, bring this inside the radical, and so I've got 1 over R, square root of L, and then this C cancels with 1 here, so it's the square root of L over C. There are many circuits that make a bandpass filter. This particular one, the value of omega naught and Q naught, depend upon our components, just like it would in any circuit. I want to sketch the magnitude and angle versus frequency. Let's take a look at the magnitude. The magnitude of the numerator is the square root of the real part squared plus the imaginary part squared, but the real part is 0, so it's just going to be this term that's right over here. Our denominator will take the real part squared, take the imaginary part squared, and then square root it. For the specific circuit that we're looking at, omega naught is 1 over square root of LC, and Q naught is 1 over R square root of L over C. This transfer function, we have two variables, omega naught and Q naught. So let me set Q naught equal to different values, and then let's sketch this response as a function of just one variable. So again, we'll vary omega with respect to a ratio with omega naught, and then evaluate the transfer function. If I let omega equal omega naught, this term drops out, and I got the same term I have here, so it's a square root of this quantity squared. If I get a value of 1 or 0 dB. Now if I plug in omega equals 10 omega naught in this expression and this one, I get a minus 19.96 dB. If I plug in omega equals to 100 omega naught, I get a minus 39.99 dB. Do 1/10, I get minus 19.96 dB, and 0.01, a minus 39.99 dB. Now sketching the actual curve, it's the dotted line that's here. What Bode realized is that you could approximate this with two straight lines. So what I see here, as the frequency increases, is a decrease of 20 dB per decade. Here I see an increase of 20 dB per decade. Two straight line segments that cross at omega naught, and the actual curve pretty much hugs those asymptotes. Now if you do this again with a Q naught of, say, 10, we get the same result for omega equals omega naught of 0 dB. So the actual curve is right here. For 10 omega naught, I get a minus 39.9 dB. For omega equal to 100 omega naught, I get minus 60 dB, and then minus 80 dB. So you can see here there's a change again of 20 dB per decade. We're decreasing with that slope. If you go the other way, a tenth, a hundredth, a thousandth for the ratio omega to omega naught, I get the same numbers. I get minus 39.9 dB, minus 60 dB, minus 80 dB. Plotting the actual curve, again, Bode approximated this as two straight line segments, kind of the parts over here, but from omega backwards, we're roughly changing at 20 dB per decade, and here we're dropping at 20 dB per decade. At the intersection of these two asymptotes, we're actually at minus 20 dB. It turns out that it's equal to 20 log of 1 over Q naught, if you go back and look at the symbolic expression. So here, the approximations by drawing the two straight lines are pretty good if you're off center here, but at center, you're going to have a gain of equal to 1 or 0 dB. Make a quick sketch of the response versus frequency with the asymptotes. Depending on the value of Q, we're going to depart right here. We don't need to calculate that point separately because that's equal to a gain of 1. The thing to note here is that as the Q naught term gets bigger and bigger, this curve gets sharper and sharper. We use these for filters to pull out a single frequency, and we'll do an example in just a little bit. I'd like to show again that the Bode plot and the circuit are telling you the same thing. So let's go back to the previous page and look at the Bode plot for a range of frequencies. I'll do the Q naught of 10 again. When the frequency approaches 0, the gain gets smaller and smaller and smaller, more negative dB. Our gain, V out over V sub s, is approaching a gain of minus infinity dB, which is equal to 0. So in other words, we're blocking the signal. On the other extreme here, if we go higher and higher in frequency with respect to omega naught, we decrease in value, so get more and more negative dB, and we're approaching again a gain of 0. And then when omega equals omega naught, we see a gain of equal to 1. Does the circuit do the same thing? When the frequency gets lower and lower with respect to omega naught as it approaches 0, this is a short circuit and this is an open circuit. So no current flows due to the open circuit. The drop across here is going to be 0 times R, or 0. As the frequency gets lower and lower, this voltage gets smaller and smaller. In the limit, as you hit DC, this becomes 0. Now what happens at the other end? As the frequency gets higher and higher, this becomes larger and larger. It's j omega L. This gets 1 over j omega c, so it gets smaller and smaller. So this approaches a short circuit as we increase in frequency. This approaches an open circuit. And the open circuit doesn't let any current flow through. We get 0 times R, and that's equal to V out. We have a very, very small output voltage. When omega equals omega naught, we'll show that the impedance of this element is exactly the same as this one, but the opposite sign. In other words, they resonate at a frequency. That'll cause a short circuit between these 2 points, and the output will equal the input. Let me do the algebra back on page 11. Omega equals to omega naught. We saw in the Bode plot that our gain was equal to 1, output equal to the input. And then for our circuit, the impedance of the capacitor is minus j over omega c, but omega equals omega naught. And likewise for the inductor, it's j omega L, but omega equals omega naught. Impedance of the capacitor is minus j over c, and then 1 over omega naught would be square root of LC. You'd think of this as the square root of c squared. One of the squares cancel with this, you get the square root of L over c with a minus j. For the inductor, we have j times L, and omega naught, 1 over square root of LC. Think of this as the square root of L squared. One of those cancels with this, and you get the square root of L over C. So these are the same but opposite signs, so their sum is 0. Again, they form a short circuit, they're resonating. The output equals the input, and we pass omega naught. Let's do an example. Suppose that I put a 2 volt peak square wave at 5.03 kilohertz with this R, L, and C, 10 millihenries, 0.1 microfarad, and 33 ohms. Resonant frequency is omega naught divided by 2 pi, and that's the square root of L times C, and that's 5.03 kilohertz. Purposely picked that frequency because of this. And the value of Q naught is 1 over R, square root of L over C, and that turns out to be almost about 10. Let's see what happens. Here's a plot of V sub s versus time. So we're going between plus 2 volts and minus 2 volts, plus 2 volts, minus 2 volts. Here's the output of our circuit. It starts out like this, and eventually starts to repeat itself. And we're seeing they're going between roughly 2.54 and minus 2.54. If you look back on pages 1 and 2, we showed that a square wave could be written as a sum of sine waves, and our primary, we call fundamental frequency, 5.03 kilohertz. And that first term in our summation was 2.54. Pulling that sine wave out of the sum of sine waves. The third frequency, we call the third harmonic, sees a very low gain. And so it's still there, it's just that it's very tiny when it's added into this result. In our AC circuits, we're seeing a steady state response. There's always a transient response that usually occurs in milliseconds or microseconds. We can't do much about this. We just simply wait for it to go away. But you really can't hear this. It's just too short in duration. But this is what it means to be a filter. You pull out a signal out of a bunch of signals. In this case, the square wave contains a fundamental frequency and odd harmonics, odd multiples of that fundamental frequency, which is 5.03 kilohertz in this example. Let me do another example of filtering. Suppose that I add 2 sine waves together, one that has a frequency of 503 hertz and 5.03 kilohertz. Both have the same amplitude of 10. Here's what the combined waveform looks like. Here's the 500 hertz signal. Here is the 5 kilohertz signal. If we pass this through the filter, we're going to let the 5 kilohertz signal through with roughly a gain of 1. And then if you go back 1 decade, the gain's approximately 1/100th. So again, there's a transient response and eventually a steady state response. I measure the period here, which the reciprocal of which is the frequency, and it's 5.03 kilohertz. 500 hertz signal is still there, it's just that it's so small you can't see it. And again, we can predict that this is going to happen by the fact that if Q naught's about 10, then if you go back a decade from the center frequency, back on page 10, you'll see that the gain is approximately minus 40 dB. So we're multiplying this 10 volt sine wave by 1/100th, and we're multiplying the 5 kilohertz by roughly 1. There is a phase response, so we'll take a look at that on the next page. To sketch the angle of our transfer function versus frequency, we'll take the angle of the numerator, but it just had a j term, and so there was no real term, so we're just going to again have the arctangent of the imaginary term divided by 0, so again that's plus 90 degrees. And then for the denominator, we're going to subtract that. It's going to be the arctangent of the imaginary term over the real term. In this specific example, omega naught and q naught have a value. Other circuits can also have different values of omega naught and q naught depending on their structure. We again have two variables here, so let's let q naught equal a specific value and then plot as a function of omega naught. Let's do q naught of 1 again. And so again, I plugged in this expression that omega equals omega naught. When I do that, when I get a 1 here, independent of q naught, that's going to again give me an arctangent of infinity, which is 90 degrees, and I'll subtract that so I get 0 degrees. So the actual curve is right here. Then if I do omega equal 10 omega naught, I get a minus 84.23. That's about over here. 100 omega naught, I get a minus 89. 0.1 omega naught, back over here, closer to 90, and then 0.01, 89.43. Here's the actual dotted curve, and Bode approximated this with 3 straight lines. One here, and one here. We're changing a total of 180 degrees in 2 decades. We're falling at minus 90 degrees per decade. This is a good approximation to the actual curve. A little bit off here and here, but don't have to compute the magnitude and angle in extreme detail, but just simply read off the graph. We'll do that for the last example. But I was doing a Q of 10, so let's take a look at that. Evaluating that equation on top, when omega equals omega naught, again, independent of q naught, you get 0 degrees. For 10 omega naught, I get minus 89.42 degrees. For 100 omega naught, I get minus 89.94. So we're going over here, getting closer to minus 90 degrees and much less change in frequency. Going backwards, we see the same result, plus 89.42 and a plus 89.94. Abrupter change in angle with frequency. Approximate this with 3 straight lines. The departure from our asymptotic approximation departs a little bit more for this dotted curve. Again, it's an approximation. For a q naught of 10, in the last example, if you go back a decade, you're pretty close to 90 degrees. And at omega equals omega naught, your angle is equal to 0. Bode plotting is an approximation to this actual curve. We only plotted a handful of points here, but there are literally an infinite number of points, and we're able to approximate those with 3 straight lines for the angle and 2 straight lines for the magnitude. And this is a bandpass filter.